And in the final part of this lecture, we will now concentrate on hadron therapy or charged particle therapy. So the therapy done with the ions, essentially. It's called ion therapy, charged particle therapy, heavy ion therapy, depending on the school. Let's say it's not easy to find a single word. So the rationale of particle therapy, of course, you remember that, I mean, is all in the physics, because the physics of the energy deposition is, of course, different. And as you remember this slide from the physics lecture, I mean, this is the depth dose deposition of, actually, this is a high energy photon, so it's 18 megavolts. So it would be worse for 6 megavolts, would be more something like that. And this is instead the Bragg peaks for carbon ions at 2 different energies, so 2 different ranges. And for protons, this is a different energy, of course, but same range of carbon. So you can now naturally from the physics get a higher dose in the target region compared to the entrance region. You also see the impact of the struggling. You have more struggling with protons, and that's why the peak is shallower, let's say, lower and broader. So if you use it, of course, the advantage from the clinical point of view will be treatment plans like that. So you see that for all organs, CNS, head and neck, lung, abdomen, pelvis, there is a comparison between IMRT and protons in this specific case. And you see that IMRT can be very conformal. So the conformality on the target is not really worse with IMRT compared to protons, but the sparing of the normal tissue is enormous, because you see that how large is the volume that you have to irradiate when you do IMRT as compared to particle therapy. Now, it is not only a matter of physics, it's also a matter of biology. So you see, this we have seen already in the radiation biology course. You know, if you compare the plateau to the Bragg, so this is the normal tissue located, this is the tumor is located. So energy, high, low, LET, low, high, depending on the particles. You know, for protons, I would say it's not really high LET, because protons cannot really have a very high LET. But if you go to heavier ions, you start to have a significant biological effectiveness here. So you see the RBE, which is about 1 here, is greater than 1 here. The OER, which is about 3 in the entrance, can be lower than 3 in the peak. Cell cycle dependence is high here, but low here. You remember the data, which means that you don't really need fractionation for redistribution in the cell cycle, because S phase is almost as sensitive as G2. Fractionation dependence is high here, but it's low here. You remember the sparing effect with the higher LET goes down. So this means that you spared, if you fractionate, you spare the normal tissue, but you don't spare the tumor. Angiogenesis seems to be increased here and reduced here. And there are many other biological effects of high-density radiation that we didn't go in details, but you remember from the fact that it's so qualitatively different brings a lot of difference also in biological effects, including the immune response that is certainly increased also with X-rays, but is probably more potent after exposure to high LET. As a consequence of this is a slide that I got from the PTCOG, which is the cooperative group of all the particle therapy centers in the world. The increase of the particle centers is really amazing. You see that this is in 2000, there were 14 centers. In 2021, we expect 140 new centers. So you see that it's like a 400% increase compared, like a 10 times increase between 2000 and 2021. So it's all in only 20 years. And the delivery of the beam is now generally done by scanning. So you see that by magnetic scanning, you can deliver a pencil beam in 2D. And then by changing energy, you can take care of the Z-axis. So you can scan the whole volume with a pencil beam in all 3 dimensions. Of course, if you do scanning, one problem that one very serious problem that you have is the moving targets, you see, because this is an example of a lung tumor, and you see not only the lung is moving, but all the abdominal organs are also moving. And what happens if you do that with the pencil beam scanning, there is an interplay between the movement of the target and the movement of the beam that produce a very poor and non-uniform dose distribution. The other problem is that, of course, you can miss the target. You know, if you don't use, let's say, a PTV as you do in photon therapy that is very big. I mean, even if you use a PTV, which is so big, the moment that you are not hitting the target, because the density of the lung is so lower than the density of the tumor, your beam will go on the other side. While this does not really happen with X-rays, which is far less dependent on the density of the target. So how do we do motion compensation and tracking? There are several techniques. We will see. Whoever of you wants to do the medical physics course, we will go much more in detail. But the idea is that, of course, the treatment planning can now be done not in 3D, because last time we saw, a few slides ago, we saw that you can do the planning on the CT scan, but you can also do the planning on the 4D CT. So on the CT done at different phase of the movement. So now you optimize the plan, not in 3D, but in 4D, including the time. You need motion detection with different techniques. You need motion tracking, so you should be able to track your motion, and treatment verification techniques like PET. PET is an excellent technique, and at the moment there is a large plan at GSI's and ERC advanced grant to study PET in combination with radioactive ion beams. A few words now on radiotherapy and second cancers. We saw this already, that actually radiotherapy it gives you a cohort of survivors. The assessment is difficult, of course, because one of the problems is that you don't really have control. Unlike Hiroshima and Nagasaki, you don't really have good control. There are a few cases where you do have control, and this is for prostate cancer and cervix cancer, where the surgery is an alternative. So you can compare surgery and radiotherapy, and if you assume that there is no increased cancer risk, second cancer risk if you do surgery, then you have a control population. The other case which is interesting is the Hodgkin's lymphoma, because in that case the risk of breast cancer is very high, it's very significant, so you can actually study. You see, things interesting, if you take prostate cancer, this is the second cancers after prostate radiotherapy, you see an increase, of course, mostly after 10 years. But the interesting part is that you see sarcoma in the field, you will wait, you will expect it, it's a very high dose. Rectum and bladder, you would also expect, because they are really in the field. Colon, you would also expect. Lung, you will not expect. So lung is a distal tumor compared to the treatment of prostate. So that's surprising. It shows that second cancer can also occur in volumes that are out of the field. One problem, of course, when you have pediatric patients is the leaking of the X-ray spectrum, because you see the leaking for a pediatric patient is, of course, much more serious than for an adult patient, because the pediatric patient is simply smaller. And even if it is a low dose exposure, you can have an increase in risk. And in pediatric patients, you know from Hiroshima and Nagasaki that they are much more sensitive to radiation carcinogenesis. And that's what we were trying to do. This is based on Hiroshima and Nagasaki. This is a map of second cancer risk for a real patient. This was a 9-year-old irradiated at the MD Anderson Cancer Center. This is the dose with proton therapy. So this is the dose. This is a medulloblastoma. Medulloblastoma requires a craniospinal irradiation. So it's a very complicated system. And you see that if you do craniospinal irradiation, you spare these organs, you will not spare them with X-rays. Actually, all these organs will be severely irradiated with X-rays. Now you can calculate the risk of second malignant neoplasia mortality and the risk of second malignant neoplasia incidence from this thing using a Monte Carlo simulation that also give you the dose here caused by neutrons. This at that time at MD Anderson, they were not using scattering. They were producing the spread out black peak using a modulator. So you produce a lot of neutrons. And you see that surprisingly, if you do a voxel-based analysis, if you look at the mortality, let's say, you see that the mortality is more here in the area of the stomach cancer and pancreas cancer than not in the high dose region. So this is interesting because eventually, if we can provide to the radiation oncologists also the information on the second cancers, that will certainly be very, very valuable. And with this, we conclude. Of course, we did very little on particle therapy, but again, this will be the topic of the other course in medical physics. Thank you.